Okay. So we're gonna keep talking about refraction. So what happens when light gets bended by going from one material to another? And this is going to be kind of short, but basically what I want to see is what happens when you have an object immersed in water, for example, and you are looking at that object. So imagine that probably you have seen this kind of trick. You have a glass of water, you put a pencil at an angle, and the pencil is kind of broken. So you probably have seen that. And so when you have a glass, you have water, you put a pencil over here, and then it looks there's going to be kind of broken. And that's basically because the light is bending, and the way we perceive the light gives us that impression that is kind of magnified and it's kind of displaced. It also happens, for example, if you are looking for something that's underwater, it usually looks to be in a different position than it actually is, or that object seems to be distorted in size when they are submerged in water. So if you think, for example, of any instrumentation that you try to design that looks at the organs inside the human body, well, you can think of it that something like that. You have something immersed in water, and when you try to create an image of that, the image is going to be distorted because light or whatever electromagnetic wave you're using, even if it's sound, is going to be distorted by the surrounding water. So that's basically what we're trying to do. And this is called image formation by refraction. That's the fancy name. And it's kind of pretty straightforward. So we're going to start using still Snell's law. So I'm going to rewrite it here. Okay, so we're going to start using Snell's law, and I'm going to assume that I have two materials. So I'm going to have water, and I'm going to have air. Okay, and I'm going to have an object at a distance s from my my interface. Okay, and somewhere around here is going to be my observer, just looking into that fish tank water or whatever. Okay. So I'm going to have my optical axis. Okay. And I'm going to have light coming from this object, and these angles are going to come at a small angle. So this is light, and I'm going to have this angle theta. Okay. And when they go through this interface, they're going to refract, they're going to bend, and they're going to come. I'm going to accelerate the angle here, and they're going to come something like this. Okay, so these rays that are in space, that are in the air, those are the ones that my eyes are perceiving. And the eyes, what they do is they're going to try to come up, they're going to try to figure out where is the origin of those rays. But because the brain cannot understand what's going on with that interface, for the rays, for the eyes, what the brain does is just trying to figure out what is the direct path. So they follow, and they imagine that they follow a straight line and what the eyes perceive is that the rays are coming from a point that is closer to the interface than it actually is. Okay? And I'm gonna call this distance S prime. And here I'm gonna have an angle theta prime. Okay, so what I need to do is to calculate that distance S prime. So I need to calculate that S prime. Okay, so what I'm gonna do is I'm gonna have this distance from my optical axis to the point at the interface where the rays are being, where the rays are incident. So I'm gonna call this distance L. Okay, I'm gonna do the first triangle just to make it a little bit clear. So I'm gonna have my optical axis. I'm gonna have this angle theta, this distance S, and this distance L. Okay, so I hope that everybody can see that here L over S is gonna be the tangent of theta. So L is gonna be equal to S tangent of theta. Okay. Similarly, if I were to do the same drawing and I were to do the same calculations using the red triangle or the prime measurements, then I'm going to end up that L is going to be equal to S prime tangent of theta prime. Okay, notice that the L, that point, is going to be the same for the prime coordinates than for the regular coordinates, for the non-prime coordinates. So these two L's are exactly the same. So, sorry, let you guys finish copying. So I can say that these two quantities are equal to each other. So I'm going to have S tangent of theta is equals to S prime tangent of theta prime. Okay, now I'm gonna do a little trick and I'm gonna assume that I'm working with the small angle approximations. And I can say that tangent of theta is gonna be very similar to sine of theta. And this will be also very similar to theta. Okay, so from here, I can say, well, then this will be S times sine of theta equals S prime times sine of theta prime. And I can use now Snell's law. N1 sine of theta 1 will be N2 sine of theta 2. Okay, so from this equation, I can, from this first equation, I can say, well, S prime is going to be equals to tangent of theta over tangent of theta prime times s, or this will be sine of theta over sine of theta prime times s. And from here, I can say, well, this will be equals to n2 over n1 times s. Let's see if I can. Okay, so remember in our drawing, we have n1 to be 1.3 and n2 was 1. Okay, so here we have s prime will be 1 over 1.3 times whatever value we're going to have. So s prime is going to be shorter than s. Okay, so it's going to look that it's closer. And because it's closer, it's going to look that it's bigger. Okay. Makes sense? Now, let's do a quick experiment. I don't think I can do it, but grab a pen, you have your pen, and you have it at arm's length. And you can see, you can close one eye, focus on the tip of your pen, and you can see that it's going to have a particular size. Okay? And you put it closer to your eyes, as close as you possibly can. The tip is going to look bigger. Okay? And if you do it correctly, like you can crush someone's head, or you can block the sun with your thumb. And that's like something very simple. The object is not getting bigger. The size of your tip of your pen is not getting bigger. It just looks bigger because the angle if I have my pen at one distance, this angle, I have theta, and if I put it closer, this angle is going to be bigger. So this increase in the angle makes it seem that it's larger. Okay, even if you're only looking at it with one eye, so it doesn't have to do anything with stereoscopic vision or anything. So this kind of magnification is called angular magnification, and it's just caused by the angle that light makes when it reaches your eye from an object. So this kind of angle magnification can be caused by a lens, or it can be caused by this change in interface, like you have light coming from here, but it appears to come from a different point, and because this angle is larger, it looks bigger. Okay. If you were able to measure that difference in magnification, will be the difference between the angles, or given the dimensions that we're using, this will be s prime over s. Okay, so let's say that you have someone standing in the bottom of a pool, and it's completely covered with water. Okay, so let's say that the refractive index of water I'm gonna say that this is gonna be 1.4. It has a lot of chlorine, and here we have air. This person has a height. The bottom of the pool is 3 meters, and this person has a height of 1.7 meters. Okay, so if you were looking from the top of this pool, I want to know what is the apparent height of this person. Okay, so first thing, we're gonna do it in two parts. First, we're gonna figure out how far the floor of the pool looks to be for the observer, and then we're gonna try to find out how far seems to be the top of the person. Okay, so remember the way we are defining these dimensions. S is going to be the distance from the object to the interface. So you want to do from the floor is the distance. S is going to be 3 meters. Da, 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 da. So this will be 1 over 1.4 over 3 meters. And that's going to be distance at which the floor is going to appear. So I'll let you guys do that. I don't have my calculator and I don't have my phone. You got it? What you got?
2.14 meters.
2.14 meters. Okay, so that pool instead of it will appear to be 2.14 meters in depth instead of the actual 3 meters. Okay, so to calculate the top of the person, it will be 3 meters minus 1.7. That will be the distance from the top of the head to the surface. Okay, so it will be from the top, that will be 1 over 1.4, 3 minus 1.7. Already, what you got? Say that again? 0.93. 0.93. Okay, so the height of this person underwater will be the 2.4 minus the 0.93. There is 1.6.
1.2.
1.21.
2.14, not 2.4.
Say that again.
It's 2.14, not 2.4.
Oh, yeah. Bless you. Okay. Makes sense? Okay, so let's do a couple more problems, not necessarily involving this refraction, but just talking about what we've been talking about for the last, from Monday and Wednesday, okay? So, Aubrey, you like horror movies?
I'm scared of them, but my brother really likes them, so.
Yeah, which one is your less favorite or the worst horror movie that you have ever watched?
I did watch Saw once.
You saw,
Saw.
I know.
That's so good.
Huh?
That's so much. Yeah, it's really scary.
Yeah, it's just like, the entire movie is just like torture.
Oh yeah, I've seen the 8 of them.
I do not like it in the slightest.
Oh, I love horror movies. I've seen all of them. Okay. Which one is the guys from Friday 13? Jason? This is Jason? Funny thing, in Mexico and in Latin America, the unlucky day is not Friday 13, it's Tuesday 13. So Friday 13, it makes no sense. Like, well, okay, I guess we're gonna see a random day, like October 27. Well, okay, that's an interesting snake. So let's say that Aubrey is escaping from Jason, okay? And Jason, and for some reason, Aubrey decided that it's a good idea to hide inside a pool. So we're gonna have Aubrey here, okay? And Jason is gonna be somewhere around here. Okay, I'm gonna say that is the same pool that we were working before. So, oh, well, it's a different pool. So I'm gonna say that this pool has a height of 5 meters. Okay. And Jason is looking at the edge of the pool, and this angle over here, I'm gonna say that this angle is gonna be 30 degrees. Okay, so you can see here what is the problem, right? So if Aubrey is on this area, she's exposed, and Jason's gonna see her, and you're gonna die. So Aubrey needs to be on this area over here, under the shadow of that eyesight. Okay, so what I want to find out, ignoring Aubrey's height, because then it becomes such a long problem. I want to know what will be this distance x. How far can she walk away from the edge of the pool before she's being discovered? Okay. I'm going to assume right now that the pool is completely empty. Okay. So there's no refraction. Light just travels in a straight line, is just at 30 degrees, and then it's just a simple trigonometric problem. This is 30 degrees. This angle is also going to be 30 degrees. And then I'm going to have that tangent of 30 is going to be opposite of adjacent. So it's going to be 5 meters over x. So x will be 5 over tangent of 30. Okay, so if you can help me really quick with that calculation.
.866.
8.66. Okay, so that's the range that RV has to height. From the wall up to 8.6 meters, we can move in that area and we'll be safe. Okay, now Jason knows physics. And then he decides, well, I'm going to start filling the pool with water. Okay, so now we're going to have a different problem. We're going to have same pool, but now half of it is going to be covered with water. So 2.5 meters is going to be covered with water. He doesn't move positions for whatever reason. So this angle is still going to be 30 degrees. But now, when light hits the interface with the water, it's going to refract and it's going to bend. Okay, so now this distance x is going to become a little bit smaller. Yeah, everyone can see that. So what I need to do is to calculate that new distance x. Okay, and I'm going to do it in two parts. First, I'm going to calculate the distance that light travels in the air before it hits the water. So I'm going to call this distance x1. And then once it gets refracted, I'm going to measure the distance that it travels inside the water. I'm going to call that x2. And then my total distance x will be x1 plus x2. Yeah. To calculate the x1, it's going to be pretty much the same thing that I did before. This angle is going to be 30 degrees over here. So x1 will be 2.5 over tangent of 30. Okay, so if you can help me with that. Say that again.
4.33.
Thank you. Oh, yeah. Okay, so that's x1. Now, to calculate x2, because light is going to be refracted, then we need to use Snell's law. Okay, now to use Snell's law, remember that we need to look at the angle along the normal incidence. So to use Snell's law, I don't need the 30-degree angle. I need this angle over here, the 60-degree angle. And what I'm going to calculate here is this angle that I'm going to call theta 2. Okay, so I'm going to have 1 sine of 60 equals 1.3 sine of theta 2. And theta 2 will be the arc sine of 1 over 1.3 sine of 60.
I got 60.
You got
60 for theta 2.
60?
Yeah.
Really? I doubt it. Christina, what you got? But you have your phone.
Oh, no, I got 41.7.
Okay, 41.7. Then I have this triangle rectangle over here. I want to calculate x2. This angle is going to be 41.7, and this side is going to be 2.5 meters. So from there, I can use tangent of 41.7 will be x2 over 2.5. x2 will be 2.5 tangent of 41.7. Riley, what you got? That again? 2.32. 2.32. So now we're going to have the total distance at which we have now to hide. X will be 6.65 meters. Yeah, makes sense. Okay, now repeat the same problem, but now imagine that Jason now covers 4 meters of the pool with water. Well, let's say that you have 4 meters of water, and Jason is now at the angle now. He's closer, so now the angle is going to be 40 degrees. Okay, so this is pretty much the same. It's just repeating a little bit of the steps that we did before. So we can divide this problem in two parts. One is when light travels in the air. The second one is when light is traveling inside the water. So we're going to have that the total distance is going to be x1 plus x2. To do x1 over x2, x1 will be 1 tangent of 40, and that's going to give me, say that again?
1.19.
1.19. And then to calculate theta 2, I need to use Snell's law. So I'm going to have n1 sine of 50. So remember, we're looking at the angle with the normal. So this angle with the horizontal is 40, with the normal will be 50, n2 sine of theta 2. And then theta 2 will be, say that again?
36.1.
36.1, and here we'll have 36.1. And x2 will be, Andrea?
I got 35.9 for mine. Maybe two.
I got 36.1, and then X2 I had 2.916.
2.16. 16?
Yeah. So 2.916.
There you go. So I will have that x will be close to 4 meters, 4.1. Yeah, Christina, what you got for theta 2?
I got 50. But I know that.
32, you got 50?
Yeah.
Yeah. You cannot get the same angle. Riley, what you got for theta 2, for the angle? Okay. Make sense? Okay, we'll do a couple more problems, not exactly the same. A very simple way to measure the refractive index of materials is just imagine that you have a slab, a piece of acrylic or a piece of glass, and you don't know exactly what kind of material it is. Okay, but you can measure the thickness of the material. So let's say that this particular material is 1.5 centimeters. Okay, and you're gonna shine some light on this thing, and there's gonna be you're gonna have light escaping the glass until you reach the critical angle, and then light is gonna just start refracting back. Okay, so if you were to see this from the top, you will see a circle over here that is a bright circle because light is coming out of this thing, and then you will see kind of dark because no light is coming out. Bless you. Okay, now let's say the diameter of this circle is 2 centimeters. Okay, and remember that the critical angle, where we said there was, let me go back. Mm-mm-mm. N1 were N2 and N1. Okay, so assume that assume that N2 is air, and what we want to find out is N1. Okay, so give it a try and try to find out what is that N1. Here's just a little bit of geometry. Find that critical angle. You got it? No idea.
No idea.
Aubrey,
No idea.
Sandy, you got it?
I'm with that.
So remember, we're gonna redraw this part. That's the critical angle. Okay, so I know that this distance is 1.5, and this distance is 2 centimeters. So can you find that angle?
Okay. Oh, because you got these guys will be 1.5. And these will be 1. So the triangle rectangle 1. So the angle that you need.
So N2 is air, N1 is the one that we want to find out. Okay, so I'm gonna go to this drawing over here, and I know that I'm gonna do this triangle. Okay, and this is my critical angle. Okay, I know that this is the thickness of the slab, so this is gonna be 1.5 centimeters, and this length over here is gonna be half of the diameter. It's gonna be, so this is gonna be 1 centimeter. Okay, so tangent of the critical angle will be opposite of adjacent, so that will be 1 over 1.5. So the critical angle is going to be the arctangent of 1 over 1.5. So you get, and that's going to be 33 point something, 33.7 degrees. So that's the critical angle. So now that I have that, I can go back to the equation that I derived from Snell's law. And I'm going to say that sine of the critical angle is going to be equals to N2 over N1. And I'm solving for N1. N2 is air, so this is just going to be 1. So N1 is going to be 1 over sine of 33.7 degrees. And you end up with 1.8, Christina? Yeah, makes sense? Okay, last problem. We have a prism, and again, it's a 30-60 prism. And I'm gonna shine a laser on it, and it goes, do it perpendicular to the first face. So remember, if you are completely perpendicular, there's no refraction. And then it comes out at an angle of 25 degrees. Okay, and I want to find out what is the refractive index of the prism. Okay, so give it a try.
The 25 is not a critic angle.
Is that the refraction?
Yeah, the critic angle is when all the light bounces back. So that's just the exit angle, just an exit angle. Okay.
Oh, shit.
Okay, we'll do this together. I think, so when you find a problem like this involving prisms, involving light being into a weird angle, the first thing you need to do is to find out what is the normal to the surface. So light is being incident at this point. I need to find out what is the normal to that point, because that's the first thing that I need to do to calculate any angle. So that normal is going to be somewhere around there. Okay, and once I have that, then I can figure out what are, or I can define what is going to be my incident angle and what's going to be my transmitted angle, my reflected angle. So my incident angle is going to be this one, and my transmitted angle is going to be this one. Yeah. Now, I can find out what is the angle of incidence and see, I'll give you 5 minutes, try to find out, well, I'll give you a couple of minutes, try to find out what is this angle of incidence. Just write it down, don't do any calculations, just, can you tell me what is that angle of incidence? Andrea? Yep, just this angle, what would be this angle? Who says 60? Who says something else? So this line is normal to this line. So between this one and this one, you have 90 degrees, right? This is 90, this is 30, this has to be 60. So if this is 60, this is going to be 30. So the angle of incidence is going to be 30 degrees. This angle is going to be the same as this angle over there. Yeah, so the angle of transmission is going to be 30 plus 25 degrees. So it's going to be 55 degrees. Okay, and now that you have the two angles, you can apply Snell's law. So N2 sine of 30 is going to be equals to N1 sine of 55. And N1 is going to be air, and N2 is what we want to find out. So N2 will be sine of 55 over sine of 30. What do you got, Audrey? Okay. Makes sense? No? Okay, we'll do more problems. I'm gonna give you some homework for next week. We're gonna keep working on this. Okay. So probably Monday we're gonna keep doing problems involving prisms and stuff.